then let's get started. Okay, so we are going to consider this electron inside a cavity. Okay. So for this one, let me just kind of step back and then let us just discuss what we talked about last time. Okay. So we start with a standing wave. Okay. So like basically we kind of made the two distinctions between traveling wave and standing wave, and standing wave just looks like this, right? Basically, it kind of looks like going upside down, right? Upside down, just like like just oscillating. It doesn't look like a travel, right? And the way you can create standing wave, the simplest way is essentially clamping both ends, right? So if you kind of fix both ends, and then you kind of like imagine that it's a string, and then if you vibrate it, it's gonna just kind of oscillate just upside down, right? And then it cannot really propagate because we are essentially clamping down both ends, right? Okay, so with that, like we basically got into how we can fit the wavelengths into this standing wave setup, okay? Like we are essentially fixing both ends, right? So basically here, like at both ends, we are essentially, fixing. Okay, and then if we vibrate this string, there will be only given conditions for wavelengths. Okay, so for example, here this example is essentially the wave that has the longest wavelengths, right? Because in this case we are essentially fitting this half wavelengths into cavity. Okay, and then the next longest wavelength is essentially, like a 1 here. Okay, 1 full cycle, and then it keeps going on, right? So if we generalize this one, we will get this expression, right? This is a wavelength, and then D is the cavity width, right? This cavity width and wavelength has this relationship. And after that, we are essentially considering an electron as a wave, and then this electron is located within this cavity, okay? And then in this cavity, like as I described before, imagine these two walls as a, like an infinite high wall, right? And then in the sense, this is why we are writing it as, like U is infinity, U is a, potential energy. Okay, this U is a potential energy. Okay, so in the sense, if electron is located within the cavity, that's a case for infinite potential 1D cavity. Okay, so then the question here is, can we find electron at the wall or outside of the cavity? The answer is, no, right? Because, like imagine, like something is in the cavity, and then if the wall is infinitely high, electrons will be only found within the cavity, right? So what that means is that, this wave amplitude, right? Wave amplitude, basically that tells you about the existence of electrons, right? So in that case, wave electron is 0 outside the cavity. That states that, like electrons cannot be found outside of the cavity. Does that make sense? Okay. So what that means is that, again, this means electron wave inside the cavity must be a standing wave. Because imagine this one, if this is a wave, if at the end, if amplitude is 0, if amplitude is 0, what does that mean? We are essentially clamping both ends. Does that make sense? Okay, because of that, the wave created within this cavity must be a standing wave. Okay, because wave amplitude is 0 outside the cavity or at the cavity, at the boundary, also at the boundary, at the wall. Okay, so what that means is that essentially we are fixing both ends at the end, within this cavity, we are creating standing wave. Okay, so then now we can use this generalized concept, right? Because for any standing waves within the cavity, it can be described as these expressions, but there can be several different types of wavelengths, right? So what that means is that now we can safely state that lambda is simply 2d over n. Okay, so I'm just expressing this one in terms of wavelengths. Okay, so here this is essentially wavelengths of electron. Okay, and n must be integers. Okay, just a 1, 2, 3. Okay, must be integers. So then now we got this wavelengths, right, for the case of infinite potential 1D cavity. And now let us consider momentum of electron. Okay, so the way we express this one is essentially mv, right, mass times velocity. And then now we are going to use lambda equals h over p. So this is essentially de Broglie wavelengths, right? This is essentially the concept we introduced last week. And then since p is expressed as this one, and then we can express this as h over lambda. Okay, so classically we express in terms of just a mass times velocity, but using a quantum concept we can express momentum in terms of Planck constant and de Broglie wavelengths. Okay, so in this case, what is lambda here, de Broglie wavelengths? We have this expression right here, lambda 2d over m, n. Now we are gonna plug it in, and it will be expressed as n times h over 2d. Okay. So, and also we are going to express energy of electron. Okay, so in this case, energy is given as 1 over 2 mv square, right? Kinetic energy. So in this case, we can also express in terms of momentum, p square over 2m. And then now we have a p expression here, right? nh over 2d. If we substitute, it's going to be 1 over 2m and h over 2d square. Okay? So now, for the case of a 1D cavity, we have momentum and energy expression. And then here, one thing important here is n is integers. Okay? So then if you look at this momentum and energy expression, you will immediately notice that these values have discrete numbers. It's no longer continuous. Okay? So for example, look at this one. Okay? So what I mean by that here is, n has to increase from 1, like a 2, 3, 4, 5, right? And then energy as well. N goes from just 1, and the next available number is 2, right? So what that means is that now if I kind of describe this momentum here, now this one has the fixed number, okay, like one value, and next it can only be these numbers, okay? So between that, momentum cannot take any values, right? So it has to be this value and the next one and the next. And then the difference between these momentum values is essentially h over 2d, right? Do you see that? And then what about energy in this case? Energy is essentially now it's going to go, when n is 1, it's going to have 1 over 2m h squared over 2d, or if you put it in the parentheses, h over 2d squared. But next one, n is 2. So in this sense, it's going to, the gap is going to increase a little bit more like that. And then, energy can only take these values, right? Not any values within, like between these two values, okay? So in the sense, here the consequence is momentum and energy is quantized or discretized. Okay? So this one is actually a very important concept, okay? And then this one is unlike a bulk object, okay? Why is that? Let us now just kind of consider the bulk object, okay? So for example, bulk object, when we consider this cavity, and then when we consider this bulk object, and then if we have infinitely high wall, and then if we put this bulk object in the kind of this cavity or bucket, how the potential or how the energy and potential vary. The potential energy, like you can locate this bulk object in any place, right? Realistically, if you just position anyone, like any height that is related to potential energy, right? So in the sense, this potential energy of the bulk object can be any values. It's really continuous. Okay. What about energy? Energy also, like this kinetic energy, 1/2 mv squared, it can take any velocity for bulk object. Okay. So in the sense, for bulk object, potential energy is continuous and energy is continuous, but for electron, or when we consider this object as a wave, now we have discretized values for momentum and as well as energy. Okay. So then the question here is, like as claimed by Juburogi, like any matter can be expressed as, kind of wave characteristic, right? And then, if we just take that, this concept, why there is discrepancy, okay? For bulk object, momentum and energy are continuous, but for this type of electron, we have discretized values. So like how do we reconcile this conflict, okay? That is essentially, like if you look at actually this expression, we can find the answer, okay? For example, look at this expression, okay? NH over 2D and 1 over 2m NH over 2D squared, okay? So for bulk object, typically this D, the cavity width is large, right? If this cavity width is large, so what that means is if D is large, what happens to delta E or delta P? Okay, energy difference, and then potential, the momentum difference here. Okay, so look at this one. So the momentum, okay, and then here NH over 2D, the energy is given as this one. If D increases here, okay, if D increases, what happens to delta P and delta E? It obviously goes down, right? So what that means is that now, if D is substantially large, what will happen to the difference? It's going to be very, very small, right? So for bulk object, because this delta E and delta P are substantially small, such that, it's essentially kind of continuous values, okay? And another fact here is, if we look at energy, 1 over 2m NH over 2D square, that is essentially 1 over 2m n square h square 4d square, right? So for example, delta E is essentially En plus 1 minus En, right? The one higher level and then the level itself, then that is essentially 1 over 2m 2n plus 1 h square over 4d square. Okay? And then, for bulk object, these are relatively large. This is why we have this smaller delta E and delta P. But another case of bulk object is, M is actually quite large, right, for bulk object. If the mass is high, what happens to this delta E and delta P? Look at this delta E. Now M goes up, delta E also goes down, right? And also, if you look at the momentum here, well, momentum does not have that here, but for energy, if we look at just M value, if we increase the mass, obviously bulk object mass has a relatively large value, and because of that, delta E goes even lower. Okay, so this is why it's making continuous value, for bulk object. But if we consider electron, let's say, if we consider electron mass is very small, right? As you probably notice, and in the case M is small, what that means is delta E is going to be appreciable, and also because electron is so small, we can relatively make a smaller cavity, okay? And then as we make a smaller cavity size, then now this D goes down, so delta E is going to be high, and now we can really notice this delta E, realistically. So that's why we have discretized energy values, okay, as opposed to bulk object, okay? So we are going to actually recover this expression using, more rigorous quantum mechanics equation. But, this is a kind of a short, kind of like a very brief discussion about why energy is discretized or quantized, which is the core concept of the quantum mechanics. Okay. So in the sense, basically from here, we are going to actually get into more rigorous form of quantum mechanics. So, the reason why we learn quantum mechanics is because this one is essential concept to understand nanomaterials or nanoscience. Okay? And also this is, a basis for modern physics. So if you want to learn about, understand modern physics, you have to know, quantum mechanics. Okay, so and later on we are going to actually get into this, but so generally, when you notice this Planck constant, okay, when you notice Planck constant in any equations, that means it has some quantum mechanical constants. Okay, so we are going to actually get into that, and then that is essentially why we have this H even in de Broglie wavelengths, right? De Broglie wavelengths is essentially any matter, right, regardless of size, whether it's small or big, it has wave characteristic, and then the wavelength of that wave characteristic is given by this de Broglie wavelength, okay, like HO over momentum. Okay, so then now let's get into a more rigorous form of quantum mechanics. Okay, so for that, we are gonna work on this Schrödinger equation. Okay. Yeah, we are going to spend some time to solve this Schrödinger equation. Okay, I mean we are not going to get into too deep, but we are going to just cover the basic concepts. Okay. So Schrödinger equation is given as minus h bar square over 2m del square this psi t and position vector and then time plus u is a potential energy. And then position vector time equals IH bar psi t over rho t. Okay. So this psi t, let me just kind of describe this equation first. This psi t is called wave function. Okay. So this Schrödinger equation is essentially telling us that wave function psi t of any matter obeys the Schrödinger equation. Okay, this one is universally applicable. Okay. So again, like probably some of you guys, may have learned about this Schrödinger equation, or some of you have never seen this Schrödinger equation. This one is essentially solving the equation for this wave function. Okay, so this wave function of any matter must obey this Schrödinger equation, and then in the sense, it's universally applicable. The size doesn't matter. Whether the size is big or small, this wave function has to obey Schrödinger equation. Okay, so and as we learn, any matter can be expressed as wave, right? That is essentially what de Broglie that's where matter wave was introduced, right? So, and then what that means is that whether you have a big object or small object, it has to obey this Schrödinger equation. Okay, but the reason why we don't use this Schrödinger equation for bulk scale object is because for bulk object, de Broglie wavelength is too small, right? Like as we calculated before. Like for example, if I kind of go back, we kind of introduce here like macroscopic object. If we calculate wavelengths, right? If we introduce this matter wave, and if we calculate wavelengths of macroscopic object, wavelength is much smaller than even atom size. What that means is that at this scale, like bulk scale object, we are not going to expect any wave characteristics. Does that make sense? So that is why, even though this one has to follow Schrödinger equation, we don't really consider any wave characteristics for bulk object. That is why, for bulk scale object, we are still dealing with Newton's law, right? Just particle constant. Because a wave characteristic doesn't exist at bulk scale object. Does that make sense? Okay. So in the sense, realistically, we are only considering small scale object like an electron, because in this case wave phenomena is very apparent, and then this one has to follow Schrödinger equation, right? This is more appropriate to discuss within the Schrödinger equation, okay? Rather than Newton's second law, those are essentially focusing on particle concept. right? In this case, wave phenomena is more apparent, and that is why we are focusing on, Schrodinger equation rather than Newton's law. Okay? Does that make sense? Do you have any questions up to this point? So again, my point here is that, like even bulk scale object, it has to follow this Schrodinger equation, but the wave characteristic is essentially none. There's no need to use Schrodinger equation for describing bulk scale object. Does that make sense? Because wave characteristic, is essentially kind of a none, or wavelength is too small such that the interference or whatever wave expect to behave cannot be observed. Okay? So in the sense, even though it is universally applicable, Schrodinger equation is exclusively used for describing very small scale objects. Okay? And then for bulk scale object, it is still fine dealing with Newton's law, right? The classical mechanics. And then here, let us look at this M. M is obviously mass. And then here, H bar is essentially H over 2 pi by definition. This is called reduced Planck constant. Okay, so H is Planck constant. Since H over 2 pi appears quite often, they just introduce a kind of new term, which is H bar. That's a reduced Planck constant. And then T is time. And then this R is the position vector. And then U is a potential energy constraint that matter is subject to. Okay, so this U is here. Okay, U is here. There's a potential energy constraint. Like you can think of this as kind of barrier. We are going to talk about that. And then this del is essentially, as you know, it's given as that. Okay, and then we have this del square there. So what that means is now if we express that, that is inner product, del inner product with the del, that is Laplace operator. Which is dou over dou x square, dou over dou y square, dou square over dou z square. Okay. So then if you look at this expression now, it has, derivative with respect to space, right? And also here we have a derivative with respect to time, okay? So this is essentially partial differential equation. And in general form, it can be, it's a 3D, right? 3D. And then, as a just introduction, we are going to deal with 1D problem, okay? Even for 1D, it can be quite complicated. So, we'll just work on 1D case, okay? So in this sense, 1D Schrodinger equation. And in this case, we are going to just work on the x direction, okay? So with that, this one will be simplified to x, and then u of x, we are going to also deal with just potential energy variation along x direction only. and psi t equals IH bar dou psi t over dou time. Okay? So, like we have to solve this Schrodinger equation to obtain this psi t, right? So, like as you know, to solve differential equation, generally, you have to guess a solution form. Okay, and then you have to check if it works, right? Once you guess, you just kind of substitute inside the differential equation and see if it works. And then once it works, you now determine unknown constants. Right? So you probably have done many times, like for 1D ODE or 2D, like a second order ODE, like often you deal with the solution form of exponential and sine and cosine, right? Probably you guys just memorize and then just substitute, but that is essentially like guessing a solution form, okay? And then you just kind of substitute and then check if it works. If it works, you find out just unknown constants, okay? So here, once we solve this equation, we will get this psi t, okay? This is like a, let me just kind of say it's obtained by solving equation here, okay? And then this psi t, okay, this is the wave function, okay? This is called wave function. But more important concept is actually psi t times psi t star, okay? So more important concept. Or parameter is this psi times psi t star, okay? This is called probability density function. Okay? This is called probability density function. And then why is this a more important concept? Because this one tells us probability to find the matter at location x, okay? Okay, so by the way, what is this star? Okay, the star is complex conjugate. So what that means is that when you have 2 plus 3i, if you put complex conjugate, this becomes, we are essentially flipping the sign for the complex number. Okay? So it is essentially the complex conjugate. Okay? So what that means is that this psi t have complex numbers, and then once you have that, if you do, complex conjugate and multiply it, then you're going to get actual real numbers. Okay? That is why we are dealing with this one, okay? Because psi t can have a complex number, it's hard to interpret complex numbers, right? And then we are essentially, taking complex conjugate of itself and then multiply that, and then we are going to get the real number, and that tells us probability to find the matter at location x, okay? So what that means is that, once you solve this Schrodinger equation, you are going to get this wave function, And then once you get this wave function, to get more physically understandable parameter, you are gonna obtain this probability density function. Okay? So once you do that, it's gonna tell us the probability to find the matter at location X. So what that means is that, it can have probability to find the matter at location 0, and it has different probability that, at different X locations. Okay? So what that means is that here it's not gonna tell us where the matter is gonna be exactly located. It's gonna only tell us the location probability. Okay? So this one is kind of a confusing concept, right? We are so used to deterministic event, deterministic quantity, right? When we solve Newton's law, it will tell us what is the exact speed, where the location is going to be. But in quantum mechanics, it's gonna only tell us the probability. Okay? It can be located at x equals 1, maybe the chance is 10%, something like that. Okay? So this is a kind of a confusing, but that is the core concept of quantum mechanics here. Okay? It only tells us just the probability, okay? Not deterministic event. And then we are going to actually talk about that over and over, okay? But for now, let us now kind of try to work on this Schrödinger equation, okay? So let me just kind of write down again here. Okay, so here, this u of x, and then psi t, the variable here, u of x is there, and then this psi t is essentially function of space and time. Okay? So when you're dealing with a partial differential equation, how do you approach the problem generally? Partial differential equation. The first step or first common one is a separation of variable, right? Have you guys worked on that? Okay. So here, separation of variables. Okay, so what we do in this case, essentially we are guessing, okay? This one, we are guessing that this one can be expressed in terms of only function of x and then only function of time, right? This essentially, we are separating into two functions, and then each function is essentially, function of just space and the function of time, okay? This is just guessing it. And then we substitute here now, right? We kind of plug this one into here and here and here or here, right? So then once we do that, now we have minus h bar square over 2m, and then psi square, not psi square, dou square, and then psi phi. Okay, so here, sorry, I'm gonna just describe as this variable, okay? Just to be consistent here, okay? Then now this psi t is gonna be expressed as this psi times v here, okay? Now we do have that here, and then dou x square plus u of x psi phi equals IH bar dou psi phi dou t. Okay. So then now, because we are using this expression, psi is only function of x, and then phi is function of time, right? And again, psi is a function of x, phi is function of time. So what that means is that now this one does not depend on, sorry, not this one. this phi is only function of time, so it can actually come out of the derivative, right? Because it does not depend on x, it's essentially constant, right? And then here we are taking derivative with respect to time, but phi is only function of x, so it can just come out of the derivative, right? Like it does not depend on time, so like it's essentially constant. So once you do that, now we can modify expression such that it's written as dx squared plus u of x psi phi equals IH bar psi d phi over dt. Does that make sense? This is how we do separation of variable. And now we divide by psi phi on both sides. So once we do that, it's essentially minus h bar square over 2m 1 over psi d square psi over dx square plus u of x equals IH bar 1 over phi d phi over dt. Okay. So now let us look at this equation now. Okay. So then let us focus on this left-hand side. And then let us focus on this right-hand side. And then if you look closely, this u is function of x, and then this psi is function of x, right? And then h bar m is all constant. So what that means is that this left-hand side is only function of only x. And then right-hand side, if you look at this one, h bar is constant, it has phi, and then it has phi, right? So what that means is now this one is function of only time, okay? So here's the question for you. Now the left-hand side is a function of only x, and the right-hand side is only function of only time. And then these two have to be always equal, right? It has the equal sign. Under what condition can this be equal? Always. Because think about this one. Function of only time. What that means is that if that is a really function of only time, as we change t, this value can change. But as we change time, does it affect any value here? No. Right? And then the same thing. This is function of only x. If we change x, this term can change, but it's not gonna do any effect on this right-hand side. Does that make sense? Then how can we make this equal? So the answer is, if this one is actually not dependent on time, and if this one is not dependent on x, then we can make equal always. Does that make sense? Because if we see actually indeed function of time, what does it mean? This value can change, while this one is fixed. Does that make sense? So this is essentially the argument where we are essentially kind of using like why it has to be constant. So this one has to be constant and in this case I'm gonna just kind of write down as E, okay? And there is a reason for that, but but argument here is this one has to be constant, some constant number. Does that make sense? If it's not constant, if it's some kind of function of x or function of time, What does that mean? We cannot really make equal always. Does it make sense? Okay, this is a, like a, probably you saw it before, like when you are using separation of variable, this concept always comes out, right? Do you guys recall? Okay, so but here, the argument here is that, if it's not constant, you cannot really satisfy this equal. Okay, so then now because of this one, the equation got much simpler. So now we are gonna just kind of express this one as one set, and then we are gonna express this as a second set. Okay, so let us look at the one set here. So now this one will give us two independent set of equation, okay, which is the from this one, okay, we are gonna express as IH bar 1 over phi d phi over dt equals E, okay, and then this one gives us d phi over dt equals E over IH bar phi, and then this one is, if I kind of flip this I minus IE over H bar phi here, okay? So this one basically gives us, or I mean, if I just express this one again, d phi over dt equals minus IE over H bar phi, and this one is essentially first order ODE, right? And then this is a one set, right? If you look at this one, that is essentially this part, and another set is this one and then constant. Okay, so let us write that as well. And for that one, let me just leave here. That is second set is minus H bar square over 2m 1 over psi d square psi over dx square plus u equals E. So in the sense, this is a first set and then second set. Okay, and then if you look at this equation, this is essentially what? That is second order OD, right? So basically, like previously we had partial differential equations, right? I mean, this one is partial differential equations, but using the separation of variable, we were able to get two different sets of equation, and then now we have, like one equation is first order ODE, ordinary differential equation, and then second order ordinary differential equation, right? So, like a partial differential equation, hard to deal with, but now, with the separation of a variable concept, we got these two easier equations, right? So this is essentially kind of what we are going to work on. And then if you look at this one first, this first order ODE, we know what the solution is. Okay, that is essentially solution. Guessing one is essentially e to the minus I e over h bar t. Okay, so that one is a general solution form, and then you can actually verify that. You can actually plug it in. Okay, this one, plug it in here, and then see what happens. So what that means is that now d phi over dt, if you just kind of plug it in here, when you take derivative, that is essentially d over dt e to the minus I e over h bar t, that is essentially minus I e over h bar e to the minus I e over h bar t. Then if you look at it, this form is exactly same as this one, right? So that is essentially how we are verifying the guessed solution, right? So and then we actually verify that this is the solution indeed, right? So that is essentially kind of a solution of first order ODE. And then this is second order ODE. Yeah, we can start solving it from tomorrow. Okay, so that's it for today. And